Welcome to the debate. Imagine trying to reverse engineer a massive, fiery planetary collision that happened, 2.5 billion years ago, using nothing but a microscopic fleck of mineral trapped in a rock.
It sounds like science fiction, right? But today, we're debating whether doing exactly that is a triumph of empirical science or, well, a massive leap of faith. We're looking at the profound challenge of reconstructing ancient macro-scale planetary dynamics, from the early architecture of the solar system to the onset of plate tectonics on Earth.
Right, and geologists frequently rely on these incredibly resilient chromium-bearing minerals, things like chromitite and ophiolite, to decode those massive events, which brings us to the central question we are framing today.
Exactly. Based on our source material, we are asking, are these microscale mineralogical indicators definitive standalone records of macro-scale planetary evolution, or does their extreme sensitivity to localized conditions lead us to completely overinterpret global and systemic models?
The debate today emerges from recent source material analyzing 2.5 billion-year-old Archean chromitites in China, the manganese-53 to chromium-53 radiometric dating of meteorites, and multi-stage chromitite genesis in the Iraqi Zagros suture zone.
I'll be arguing that extrapolating global dynamics from these highly localized, context-dependent micro-recorders is methodologically perilous.
And I contend that these chromium-based structures are unparalleled, definitive time capsules that reliably prove large-scale models.
Okay, we'll lay out the case for the time capsules then.
Gladly. I mean, chromium-bearing minerals and their isotopes provide hard, empirical constraints that can definitively confirm or overturn major theoretical models. Take the 2.505 billion-year-old Zhenhua podiform chromitites in the North China Craton.
The podiform chromitites?
Right. Yeah, because chromite becomes incredibly rigid at high temperatures, like cooling below 1200 degrees Celsius. It perfectly preserves delicate magmatic flow textures. Things like nodular and orbicular textures from the upper oceanic mantle.
The preservation is amazing, I'll give you that.
It is, and it offers undeniable physical proof of Archean plate tectonics. But wait, it's not just Earth. There's a recent breakthrough in dating ophiolite in chondritic meteorites. It pinpointed aqueous alteration to just 2 to 4 million years after the solar system formed.
Using the manganese-chromium stopwatch.
Exactly, which provides hard data that physically places asteroid accretion right in the inner solar system.
Right, but, while these minerals are exceptional micro-recorders of local environments, using them to validate sweeping macro dynamics is fraught with complexity. It's incredibly fragile methodologically.
Fragile? How so?
Well, I acknowledge the resilience of chromite, sure, but look at the Iraqi, Qalandar, and Rayat Ophiolites from the source material. You find entirely different tectonic signatures there. High-Al MORB affinity right next to high-CR bonanitic supersubduction affinity within the exact same mantle section.
Which just shows a very dynamic environment.
It proves these minerals record complex, localized, multi-stage events, not simple, uniform tectonic settings. And that ophiolite dating you just brought up?
Yeah.
The 3 million-year timeline shift required synthesizing a custom FON 99 standard in the lab, because traditional standards yielded a 60% discrepancy in the relative sensitivity factor. If sweeping planetary models hinge on such microscopic matrix corrections, our macro conclusions are resting on a knife's edge.
I would argue that identifying and correcting that bias is a massive strength, not a weakness. But let's go back to the Archean Earth evidence first, because the physical preservation directly addresses your concern about localized chaos. The Zhenhua chromites act exactly like an airplane's black box.
A black box?
Yes. Look, even though the surrounding ophiolite was destroyed and ground into a melange during a collision between the eastern and western blocks of the North China Craton, the rigid dunite-enveloped pods preserved pull-apart and anti-nodular textures.
I know that textures survived, but
just as a black box survives a crash to tell you exactly how the plane was flying, these chromite pods definitively tell us seafloor spreading and mantle flow were operating 2.5 billion years ago.
A black box records the local mechanics of one specific plane. It doesn't tell you the global state of the entire aviation industry.
That's a bit of a reductive analogy.
Is it? You're looking at Zinhua blocks that are essentially isolated tectonic boudins, deeply embedded in a highly deformed biotite gneiss matrix. Yes, they record flow, but we have to fundamentally question whether localized mantle melting in a potentially hotter Archean Earth definitively equates to global, uniformitarian plate tectonics.
It's not just a random hotspot, though. The textures themselves physically require the partial melting of a flowing upper mantle.
Local convection can happen without.
But you can't fake the fluid mechanics of an oceanic spreading center. That flowing motion is the actual mechanism of plate tectonics. You simply cannot have a local hotspot mimic those exact mechanics without the systemic machinery driving it.
You can have isolated flow without a rigid global plate network. But, okay, let's move from the interpretation of physical textures in Earth's mantle to those isotopic ratios in early solar system asteroids, because the scaling problem is just as severe there.
I completely disagree. The ophiolite evidence is incredibly robust. When you look at the thermodynamic modeling of that meteoritic ophiolite, it shows it formed at low temperatures, like 100 to 200 degrees Celsius.
Right, with very low water-to-rock mass ratios, around 0.1 to 0.2.
Exactly. It barely got wet, and it didn't get very hot. And this explicitly places their formation in the inner solar system, around 2 to 4 AU. Which means sweeping gravitational theories like the Grand Tack model, which requires these bodies to form way out beyond Jupiter and migrate inward, are simply not required.
Okay, the 53MN53CR dating of the Elephant Moraine and Osca meteorites is highly precise. I am not debating the machine's readout.
Then what is the issue?
The issue is the massive scale of the conclusion you're drawing. Are we really saying that localized aqueous alteration in a specific, tiny subset of chondrites is sufficient evidence to completely dismiss a system-wide planetary migration model?
If the physical data contradicts the model, yes.
But the Grand Tack model solves multiple orbital mechanics problems like the small mass of Mars and the actual structure of the asteroid belt. You're letting one localized drop of water in a meteorite override the gravitational dynamics of Jupiter.
We aren't overriding Jupiter's dynamics. We are anchoring our models in tangible reality rather than pure simulation. If the physical samples in our possession don't require the Grand Tack to explain their hydration, the simplest explanation is they formed where their chemistry dictates.
But the chemistry you are anchoring this to is built on an incredibly delicate laboratory procedure. The entire revision of this asteroid timeline relied on correcting a massive instrumental bias in how the mass spectrometer reads the atoms.
You're talking about the matrix effect.
Yes, because the ionization efficiency of the manganese-55 ion differs significantly from the chromium-52 ion depending on the iron content in the olivine.
Wait. Let's break that down for a second so we're absolutely clear. You're saying that the very machinery we use to read the isotopic stopwatch gets confused and runs at different speeds if there's too much iron present in the rock?
Exactly. Researchers realized that using a standard test matrix with low iron produced skewed dates for ophiolite, which is packed with iron. They had to manually synthesize a custom Fa99 ophiolite standard to correct a 60% bias in the machine's sensitivity.
Which they caught and corrected?
But the extreme sensitivity of these isotopic ratios to the mineral matrix makes macro extrapolations inherently unstable. It's like looking at a single pixel of a photograph and trying to confidently declare you know what the entire billboard looks like. One slight tweak in how we synthesize that standard in the lab, and suddenly Jupiter is migrating again.
I mean, identifying and correcting a 60% relative sensitivity factor bias is a triumph of empirical rigor. It's not a weakness. It proves our tools are finally sharp enough to adjust for the matrix effect.
It proves the system is fragile.
No, it proves we can be precise. We see this exact same level of necessary precision in the Iraqi chromitites. The discovery of osmium-rich laurite inclusions in those rocks required precise microprobing.
Right, probing grains that were less than 5 micrometers across.
Exactly. And it revealed that the parent magma was sulfide undersaturated. The refinement of our microtools is exactly what allows us to filter out the noise of local variations and see the true macro picture. We need that microscopic precision to build the big models.
But the microprobing in the Iraqi Ophiolites revealed highly complex, contradictory local environments, mid-ocean ridge signatures sitting right next to subduction zone signatures. That implies a chaotic, constantly shifting local environment, not a neat, uniform global process. The precision highlights the chaos, it doesn't resolve it.
Look, to summarize my position in light of our discussion, despite the sheer chaos and complexity of geological and planetary history, chromium-bearing minerals provide unparalleled, unyielding physical and isotopic data points.
Even when they're isolated fragments?
Yes, because whether they are preserving 2.5 billion-year-old mantle flow in a rigid envelope or tracking the exact timeline of asteroid hydration via precise isotopic decay, they remain the hardest empirical constraints we have against purely theoretical models.
Well, to summarize my view, while the fidelity of these micro-recorders is undoubtedly stunning, the debate today reveals how easily we conflate highly specific, localized conditions, like a single faunine stander or a mixed-melt chromitite pod, with universal planetary models.
So the map is not the territory.
Exactly. The map is not the territory. We must be cautious not to let a brilliantly detailed microscopic snapshot convince us we have perfectly deduced the entire multi-billion-year movie.
There is clearly a persistent, beautiful tension here between the astonishing precision of micromineralogy and the incomprehensible scale of planetary physics.
Absolutely. And there is so much more to explore in the source material regarding how we scale our understanding from the atomic level all the way up to the solar system level.
So we leave it to you to form your own conclusion. Thanks for joining us on the debate.